This rocket launched the Pioneer 10 probe into outer space. It is the first such projectile to leave our solar system. Its journey will last for over 1,000 years. Should some form of intelligent extraterrestrial life happen to discover it on its way, it will find a gold-plated aluminum plaque mounted on it. It contains information about our planet, a diagram of a hydrogen atom, our position in the universe.
Actually, it's a link along that tether line you see there, 25 feet of umbilical cord. That contains the life support system and communications link.
To stay, risks annihilation. It could be an asteroid hitting the Earth. It could be a new virus, climate change, nuclear war, artificial intelligence gone rogue. We can, and must, use our curiosity and intelligence to look to the stars. We must do it now before humanity is overtaken by some disaster that we can neither anticipate nor control. I have no doubt that we will eventually find ways of crossing the immense distances of space in just a few years.
One of our species' great strengths is embracing new ideas and evolving them into cutting-edge technologies. Just look at advances we've made in the fields of medicine, communications, and electronics. We only built the first silicon chip 60 years ago. Now it powers just about every aspect of our lives. Our ingenuity will get us to Proxima B.
But I think the development of full artificial intelligence could spell the end of the human race. We can, and must, use our curiosity and intelligence to look to the stars.
Stephen Hawking, a renowned theoretical physicist, wasn't just known for his groundbreaking discoveries in cosmology and black holes. He also shared his concerns about the future of humanity, touching on various topics with his characteristic scientific insights and their potential impact on society. Here are some of the fears and concerns he expressed for the future of humans. One of Hawking's concerns was the threat of asteroid impacts on Earth. This isn't just science fiction, it's a real possibility that has happened before and could occur again if we don't take preventative measures. Asteroids are rocky remnants from the formation of our solar system, and while most are found in the asteroid belt between Mars and Jupiter, some have orbits that bring them closer to Earth, making them near-Earth objects. The most famous historical example of an asteroid impact is the Chicxulub impact, estimated to have occurred 66 million years ago. This colossal event is widely believed to have caused the mass extinction that wiped out the dinosaurs and roughly 75% of Earth's species at the time. The impact created a crater roughly 150 kilometers wide in what is now the Yucatan Peninsula in Mexico, and the environmental changes it triggered, including widespread fires, tsunamis, and a nuclear winter caused by dust blocking out the sun, showcase the potential catastrophic consequences of large asteroid impacts. While most near-Earth objects are small and harmless, burning up in the Earth's atmosphere, larger ones could cause significant damage upon collision. The level of threat depends on the size of the asteroid, with larger ones potentially causing regional or even global disasters. Thankfully, efforts are underway to protect Earth from asteroid impacts. The first step is detection and tracking. Several programs like NASA's Near-Earth Object Observations program are dedicated to discovering and monitoring objects. These programs use ground-based telescopes and space-based sensors to track the trajectories of asteroids that could potentially impact Earth. Fortunately, scientists haven't just identified the threat, they're also exploring ways to deflect or mitigate potentially catastrophic asteroid impacts. One method involves a spacecraft essentially playing cosmic bumper cars. The kinetic impactor technique involves launching a spacecraft to deliberately crash into an asteroid, ever so slightly altering its trajectory and nudging it away from Earth. An example of this technique being tested is NASA's DART mission, aiming to practice this method on a smaller asteroid. Another approach is the gravity tractor method. This strategy involves a spacecraft slowly flying alongside an asteroid for a long time, using its own gravity to gradually pull the asteroid off course. Nuclear explosions are a more controversial option. The idea isn't to blow the asteroid to smithereens, which could create multiple smaller threats, but to use a precisely detonated nuclear explosion near the asteroid to create a powerful push, altering its course. The good news is that we're not facing this challenge alone. The international community recognizes the global threat posed by asteroids. The United Nations has established organizations like the International Asteroid Warning Network to share information about potential threats, and the Space Mission Planning Advisory Group to coordinate international efforts in deflecting dangerous asteroids. For example, an asteroid named Apophis gained notoriety for its potential to hit Earth in 2029 or 2036. Thankfully, further observations have ruled out any impact threat from Apophis for at least the next 100 years. While not an immediate danger, close encounters like these offer valuable opportunities for scientists to refine their tracking and deflection techniques, ensuring we're better prepared for any future threats that may arise. The search for extraterrestrial life is in full swing, with scientists using telescopes to listen for possible signals from distant civilizations. But amidst this excitement, Stephen Hawking offered a word of caution regarding the potential dangers of contacting aliens. His concerns, while thought-provoking, are part of a larger conversation about the possible consequences of encountering life beyond Earth. SETI projects aim to detect signs of intelligent life by searching for radio signals that could be of artificial origin. Additionally, the Messaging to Extraterrestrial Intelligence initiative seeks to send messages into space in the hopes of establishing contact. However, Hawking's viewpoint urges us to consider the potential risks involved. His perspective is influenced by the precautionary principle, which essentially states that when the potential consequences of an action are unknown, it's best to err on the side of caution. Applied to contacting aliens, this principle implies that without understanding their intentions or capabilities, we should proceed with caution. One of Hawking's concerns is the possibility of encountering a civilization far more advanced than ours. He points to the concept of the technological singularity, a hypothetical point where technological advancement becomes rapid and unpredictable. Extraterrestrial civilizations that have reached this stage might possess unimaginable technologies, potentially including methods of interstellar travel, advanced energy manipulation, or even control over the fabric of spacetime. Furthermore, Hawking mentions von Neumann probes, self-replicating spacecraft theorized by some as a means of interstellar exploration. If such probes are designed to acquire resources, Earth could become an unwitting target, highlighting the potential dangers of resource depletion in space exploration. Beyond technological risks, Hawking also raises concerns about unique type of consequence. He draws a parallel to the Columbian Exchange, a historical period where the introduction of foreign plants, animals had devastating effects on indigenous populations in the Americas. An encounter with aliens could lead to similarly unforeseen and potentially catastrophic consequences. The theory of directed panspermia adds another layer of complexity. This theory suggests that life on Earth may have been deliberately seeded by an advanced civilization. While speculative, it raises the possibility of contamination in both directions, with not only Earth's biosphere being at risk from alien organisms, but also the potential for us to unintentionally harm extraterrestrial ecosystems. Hawking's cautionary words, while not a call to abandon the search for extraterrestrial life, encourage us to approach potential contact with an open mind, but also with a healthy dose of prudence and awareness of the potential risks involved. Our quest to find out if we're alone in the universe has sparked a multitude of fascinating theories and concepts. Stephen Hawking had some interesting ones. Here are a few that attempt to answer the age-old question, are we truly alone? The zoo hypothesis takes a hopeful approach, suggesting that advanced alien civilizations might be observing us, like specimens in a cosmic zoo. This theory implies a sense of responsibility and non-interference on their part, perhaps similar to the concept of a prime directive in science fiction. However, the zoo hypothesis also presents challenges for the search for extraterrestrial intelligence. If aliens are actively hiding or avoiding contact, SETI might need to go beyond just searching for signals. They might need to look for subtler signs like evidence of observation or manipulation from these advanced beings. This concept ties into the idea of the anthropic shadow, which suggests our observations about the universe are inherently biased. We might only see what allows for our own existence. If civilizations readily expose themselves or interact carelessly, they might not survive long enough to be observed, making the silence seem deafening. On the flip side, the dark forest theory paints a much bleaker picture. It imagines the cosmos as a dark and dangerous place where every civilization acts like a silent hunter, fearing to reveal their location to potential threats. This theory, inspired by science fiction, is based on the idea of cosmic sociology, exploring how civilizations might interact based on survival and risk. The dark forest theory delves into the chilling concept of cosmic loneliness. The vast and silent universe, it suggests, could be a result of civilizations' fear of annihilation, driving them to hide rather than seek contact. This theory also introduces the chain of suspicion, where even without direct hostility, mutual distrust and fear can prevent civilizations from reaching out, leading to a preemptive strike mentality and further discouraging open communication. The Fermi paradox highlights the seemingly contradictory nature of our situation. The probability of extraterrestrial life existing appears high, yet we have no concrete evidence to confirm it. This paradox has led to several other thought-provoking speculations beyond the zoo and dark forest theories. One such theory is the Great Filter, suggesting there might be a critical and potentially unsurpassable stage in a civilization's development that prevents them from reaching a point of communication with others. This hypothetical hurdle could be something we've already overcome, like the origin of life, or something we might face in the future, like managing advanced technology. Another interesting speculation is the transient hypothesis, which proposes that civilizations might be fleeting, quickly evolving beyond the need for detectable communication methods, or even succumbing to self-destruction. Finally, the Drake equation offers a scientific framework for estimating the number of active communicative civilizations in our galaxy. While the equation itself is relatively simple, the values it uses are highly uncertain, resulting in a wide range of possible answers. The search for extraterrestrial intelligence has also expanded its scope beyond just radio signals. Inspired by the Drake equation's focus on communicative civilizations, scientists are now searching for other technological signatures, such as the effects of large-scale engineering projects or unusual energy consumption patterns. Additionally, discoveries of exoplanets in habitable zones and extremophiles on Earth are prompting revisions to the Drake equation's variables, suggesting a potentially higher chance of life existing in the universe. The search for extraterrestrial intelligence is a captivating journey fueled by scientific inquiry and our inherent curiosity about the universe. These various theories and concepts, while speculative, offer a glimpse into the different perspectives and possibilities surrounding the existence of life beyond Earth, keeping us engaged in our ongoing exploration of the cosmos.
The thing about Oumuamua is that it was the very first object that visited from outside the solar system. You have some anomalies, some things that don't quite match what you expected, and you're trying to find an explanation.
Ever since its discovery in 2017, Oumuamua, the first confirmed interstellar object to visit our solar system, has been captivating scientists. Its unusual nature and mysterious origins have sparked countless studies and theories, making it a landmark discovery in our understanding of the universe. Oumuamua's story began on October 19, 2017, when astronomers in Hawaii, using the Pan-STARRS 1 telescope, designed to spot near-Earth objects, stumbled upon something unexpected. Robert Werrick, a researcher at the University of Hawaii, noticed the object while analyzing data from the telescope. Unlike anything else in our solar system, Oumuamua didn't resemble typical asteroids or comets. News of the discovery spread quickly, and astronomers worldwide trained their instruments on the object. Their observations confirmed it wasn't bound to the Sun by gravity, revealing its interstellar origin. The object was then named Oumuamua, a Hawaiian word chosen by the Pan-STARRS 1 team with the help of language experts. It translates to a messenger from afar arriving first, reflecting its unique status as the first known visitor from another star system. The naming of Oumuamua held significance beyond the object itself. It acknowledged the contribution of Hawaii and its people to astronomical discoveries. While initially classified as an asteroid due to its lack of a visible coma or tail, Oumuamua's unexpected acceleration as it left our solar system threw scientists a curveball. This behavior is characteristic of comets, which expel gas and dust for propulsion, but Oumuamua displayed none of the usual signs. One theory suggests Oumuamua might still be outgassing, but invisibly. The release of a small amount of gas or dust undetectable by telescopes could explain the acceleration, making it a new type of comet without the usual visual cues. However, Harvard astrophysicist Avi Loeb took things a step further with a more controversial theory. Oumuamua could be an artificial object, possibly a light sail from an advanced alien civilization. He cites its unusual shape, shiny surface, and unexpected acceleration as evidence against a natural origin. Loeb suggests Oumuamua's high-speed, sun-grazing trajectory and sudden acceleration could be explained if it were a probe or light sail, a thin sheet that uses solar radiation for propulsion. While captivating, this theory is highly speculative and lacks broad scientific acceptance. Scientists have proposed several alternative explanations within the realm of natural phenomena. One theory suggests it could be a fragment from a disrupted planet or other celestial body, which could explain its unusual shape. Another interesting theory proposes it as a hydrogen iceberg, composed of molecular hydrogen ice. As it neared the Sun, the ice sublimated, transforming directly from solid to gas and providing thrust without a visible tail. However, the feasibility of such an object surviving interstellar travel remains debated. Some researchers also believe it could represent a new class of interstellar object, formed through unknown processes. Its characteristics might be typical for objects ejected from other star systems, potentially leading to the discovery of more similar objects in the future. Oumuamua's extraordinary shape, far more elongated than any known object in our solar system, has captivated scientists. Estimates suggest it's roughly 800 meters long and 80 meters wide, with a remarkable 10:1 aspect ratio. Determining the exact shape is challenging due to limitations in observing such a distant object. Unlike most solar system objects, Oumuamua exhibits a tumbling motion, hinting at a possibly violent past. It also shows a non-gravitational acceleration as it moves away from the Sun, a phenomenon not fully explained by the Sun's gravity. The dark reddish surface, similar to some outer solar system objects, suggests the presence of organic molecules. This, along with its color and other characteristics, points towards a composition similar to comets and objects beyond Neptune in our solar system. The long journey and exposure to cosmic rays could explain the darkened surface, potentially masking its original composition. While the investigation continues, these unique characteristics offer valuable clues in unraveling the mystery of its origins. Oumuamua's journey through space is estimated to have spanned billions of years, leaving its mark on its surface. The object's dark reddish color is a telltale sign of prolonged bombardment by cosmic rays, which can alter the chemistry of interstellar objects over time, creating complex organic molecules. This long exposure to the harsh environment of space suggests a lengthy voyage through the vast interstellar medium. Remarkably, the frigid temperatures and near-vacuum conditions of interstellar space can act as a natural preservative. Unlike objects within our solar system exposed to solar radiation and atmospheric wear and tear, Oumuamua's surface may have remained largely unchanged since its ejection, offering a potential glimpse into its original state. Scientists are piecing together the puzzle of Oumuamua's path using a combination of observations and simulations. They analyze data on the object's position, speed, and acceleration during its passage through our solar system, factoring in the gravitational influences of the Sun, planets, and other celestial bodies. One key concept is the gravitational slingshot effect, where an object gains speed by passing close to a massive body. By calculating the cumulative effect of such encounters during its journey through our solar system and backtracking through time, scientists can chart a possible course for Oumuamua's arrival. Several studies have attempted to identify stars or systems Oumuamua might have encountered during its travels. Some possibilities include young star clusters and even specific stars like HIP 3757 and HD 292249, which had close approaches to Oumuamua's trajectory millions of years ago. However, pinpointing the exact origin remains a challenge. Uncertainties in Oumuamua's velocity and the dynamic nature of our galaxy, where stars are constantly moving, make it difficult to trace its path with precision. Any non-gravitational acceleration, like that potentially caused by outgassing, further complicates the calculations. As Oumuamua ventures through interstellar space, it interacts with the interstellar medium, a sparse collection of gas, dust, and charged particles. While seemingly insignificant, this medium can exert subtle forces on objects over immense timescales, potentially altering their trajectories. These subtle influences, like drag from dust or gravitational tugs from unseen matter, add another layer of complexity to reconstructing Oumuamua's long journey. Despite the challenges, Oumuamua's interstellar origin, confirmed by its unique trajectory, makes it a valuable visitor. It offers a rare opportunity to study material from another star system, providing insights into the composition and formation of objects beyond our solar system. Ever since its discovery in 2017, analyzing its trajectory and speed has been crucial to understanding its path and future. Unlike planets and most objects in our solar system that follow closed elliptical orbits, Oumuamua is on a hyperbolic trajectory, an open path taking it permanently out of our system. After a close encounter with the Sun, it gained enough speed, roughly 26 kilometers per second, which is about 58,000 miles per hour, to escape the Sun's gravitational pull. Currently, it's journeying towards the constellation Pegasus and won't be returning anytime soon, so we think. As an interstellar object, Oumuamua's journey through our solar system was a brief stopover. Its immense speed ensures it won't be captured by the Sun's gravity, meaning no return visits are possible. Extensive calculations confirm this one-way trip, with Oumuamua destined to become a permanent wanderer among the stars in the Milky Way galaxy. Scientists have meticulously analyzed Oumuamua's trajectory. Its hyperbolic path, unlike the closed orbits of planets, signifies its interstellar origins and independence from the Sun's gravitational influence. Furthermore, its speed and the direction it entered the solar system, originating near the constellation Lyra, couldn't be explained solely by interactions within our system. While the object's age and the vast distances involved make pinpointing its exact source challenging, tracing its entry point provides valuable clues about its potential home. So will Oumuamua return? Not in our lifetime, but maybe another one. Understanding Oumuamua's trajectory unveils its journey as a one-time encounter and underscores its status as a permanent ambassador from another star system, offering a glimpse into the wonders beyond our solar neighborhood.